All right. Greetings, everyone. Welcome to chapter 3. We're going to talk about probability today and sampling distributions and sampling methods. So it's not super complex stuff, but it's good. It's more good groundwork for us as we move through, the rest of our semester. So let me share my screen with you, and we'll walk through the PowerPoint together. There we go. So not super complicated stuff today with probability. Probability can become complicated, um, just like any other process, the more you learn about it. But for the sake of our class and what you guys need to know, is we're going to do some, you know, very, very simple proportional probability for our class. And there are other forms, but we're just going to stick to one because it's what we need for our class. And the idea is that this is a groundwork, foundational chapter for us as we proceed later on in the course, really in the second half, when we start doing hypothesis testing. Then probability becomes really, really important because we want to know, what is the probability of an event occurring versus the probability of an event not occurring just by chance. So it's like saying, what's the likelihood of something happening? Well, that's difficult to measure, and we'll talk about some of those things today. All right, so here we go. Almost some more core foundational knowledge for the rest of our stats class. The first thing I wanted to go over is just some learning objectives for this chapter. Just so we're on, this on the same page. Here's our roadmap. We're going to look at the role of probability in selecting a sample from the population. There's different ways to do that, and uh, we'll just go over some. What is it? I got like five or six basic ways that's done, and we'll talk about the advantages and disadvantages and kind of situations where you might use one technique for creating a sample versus another. Um, so that kind of gets into learning objective number 2 as well. And then we'll talk about understanding the distribution of sample means. We're not going to do a whole lot with that in this chapter, but that will become really, really important, later on when we get to doing more calculations. So I'm just going to kind of get your feet wet today with the distribution of sample means. And then also with the idea of, like it says here, we can estimate the population values from a sample. So we can talk just a little bit about that too. And we're just trying to get your feet wet with probability today, and we'll put it in action more in chapters further down the road. Okay, so just a reminder. The first thing that we're going to talk about is going from a population to a sample, and then right there where it says selection, it's like, okay, well, how do you select? Of course, the goal for all of the different selection processes is to have as little as bias as possible, because we want representative samples, right? Representative of the population. If it's not, right, if there's something that goes wrong, and that means you have something called sampling error, that means that something about your sample, um, like the individuals in your sample have too much in common, so it's going to skew your results, right? Of course, we don't want that to happen. So what kind of techniques can we use to ensure that doesn't happen, or at least to minimize the amount of sampling error when we're creating a sample? And so, for example, if you were to say you had some new, I don't know, some new kind of drug, and you said, okay, people take this drug, it will increase their IQ, and you want to test that on people. And so you select a sample of people from the population, and maybe you go to a college, and at that college, you just put like a sign up sheet on a bulletin board, like sign up for this, psych study about intelligence, and people volunteer their time to sign up. Well, what if, let's say, you collected data from 100 people, and just like 90 of them were already those that had a really, really high IQ? Well, that would be problematic, wouldn't it? Because then if you administered your drug in an experiment and you go, man, look how high their IQs are now, they may have been high to begin with. And so that would be sampling error. You would say, oh man, look what my drug did. But in actuality, um, you're lacking some validity there. And some reliability too, because that sample already had a high IQ. So kind of like there's like bad luck, you could say, when it comes to selecting your samples. So of course we want to find different ways to prevent that from happening or minimize that amount of error as much as possible. right? Because all, just like the last chapter we talked about this, I think it was the first chapter, where we said, okay, we can draw an average score from our sample, then we make an inference back to the population, and those two numbers should be the same. If they're not the same, then there's some kind of sampling error, present, um, and maybe your sample is not representative of the population. So something to consider there. Okay, now so there's some new statistical notation for this chapter. There's not a whole lot, honestly. So I thought I would go over some language with you, really. So here's something to think about. If the word probability kind of stresses you out because it makes you think of statistics, well, think about these other words instead that we use, probably more regularly. Um, but they essentially express the same concept just in a different way, right? It's like there's a different languages around the world, but they can all express the same sentiment, right? So for example, if you're talking about the word odds, you're saying, okay, this is a fraction or a ratio. So if you were to say, okay, what are the odds that if I have a six-sided die, like in the picture here, what are the odds that I roll a six? You would say 1 in 6, because there's only one number six, and there are six, potential outcomes, six possibilities if you roll the die at random. So there's a 1 in 6 odd that you would get a six on your first roll, right? And then chance, that's probably how we speak more, right? We speak more in terms of chance. So if you said, all right, what's the chance that I would roll a six, the first time you roll a die, then you would just do like a real simple, mathematical formula to figure that out. So you would say, okay, well, there is one outcome that I'm interested in, rolling the six, that's the one, and divided by the possible outcomes, there are six different outcomes. So you do one divided by six, and then your chance comes out to basically a 17%. So you have a 17% chance of rolling, a six on your first roll of the die. So that's pretty good because it gives us a percentage, and we're using the word chance. So most of us are pretty comfortable with that language, but you might not have given that much thought, into like how you figure that out mathematically. It's not complicated, but once you get the gist of calculating odds, chance, then probability is kind of the same thing. You just leave your answer as a decimal. So if the chance of rolling a six on your first try is a 17%, then the probability is just that in decimal forms. You'd say 0.17, right? All right. Now, here's the new notation. So the symbol for probability is P, and you can put that in a sentence, and I'll give you an example. So here's one in notation form. Like, it probably doesn't make any sense, and that is okay, right? We're just going to talk about this for a second. So if you're looking at this, P in the parentheses, you have X is greater than 4 equals question mark. Well, that's a mathematical question you're being asked in this case. So what is the probability of rolling a score greater than 4? So here's the basic idea in a nutshell. Let me switch my camera view to my whiteboard. Right. So let's say that the question was, what is the probability of randomly rolling the die and getting a score that is greater than 4, right? That was the question. So we're going to take how many outcomes there are on the die, and there's 6 different outcomes, and then how many of those are greater than 4. Well, there's a 5, there's a 6, so 2/6. We could break that down if we want to talk about terms of odds. So here are the odds: 2 out of 6. We could simplify that and say 1 out of 3 odds, right? Or you might see it like written like that, right? So that's all the way you express odds. Now, if you were to say chance, remember chance is a percentage. So in that case, we would do 2 divided by 6 or 1 divided by 3 should give us the same answer. So let's try that out. Here's my calculator. So we'll just do about 2 divided by 6 equals 0.33, right? So we would say, all right, well, this was a question about this is odds. And then we wanted a question about chance. Then we would do 2 divided by 6 equals roughly 33%, right? And that's how you would express the same problem in terms of chance, right? And then for probability, it's this kind of the same thing, right? You just do 2 divided by 6 equals, we know it's going to be 33%, but we're going to leave it as a percentage. And then there you have probability. Right? So pretty easy stuff. The way to think about it is like calculating simple probability is, in your denominator you have all of the possible outcomes that can occur, and on top you have just the outcomes that you're interested in. And if you're talking about odds, you just leave it in this fraction form. Talking about chance, then you express it as a percentage, but you divide the two to get it. And if it's a probability, then you express it, your answer, in terms of decimals, but it's the same process. You do 2 divided by 6 to get that answer, right? Really simple. So just remember, the outcome of interest goes on your denominator, right, on the bottom, and then what you're interested in measuring for goes on the top. And then you divide. Even if the numbers are much greater than 2 and 6, it'll be the same process. Okay. It'd be the same thing if you wanted to do, we could do it one more time, for the probability that your x is less than 5. So let's just run through that one more time, just for the heck of it, for practice. So the probability that your x value is less than 5. So that means it looks like this. We've got probability x is less than 5. So the question really is, what's the probability of getting a score less than 5 at random or by chance? So if it's die again, let's say it's die, there's still 6 possible outcomes. And then how many scores are less than 5? Well, there's 4 of them, right? 4, 3, 2, and 1, all less than 5. So we could say, all right, it's 4 out of 6, or it's 2/3, or 2 out of 3. And that would be how you express, this problem in terms of odds. And then the other way to look at it, right? Say, okay, there's 6 possible outcomes. And if we do 4 divided by 6, then we get 0.66667, right? So we can round that up to 0.67. So it would be 67% if we're talking about chance. And then if we're talking about probability, which is what we're going to do in this class, then I want you to start practicing expressing these answers as decimals, right? But I wanted to point out that it's really the same process. If you're computing something for chance or for odds, mathematically you go through the same steps. We just use different language to talk about, how we want the outcome presented: decimal, percentage, proportion, as a fraction. Okay, pretty easy, right? Okay. Oh, here we go. Here's a little formula for you that I was just talking about. So you're in your numerator on top, you have the outcome of interest, and then you have all possible outcomes. All possible outcomes go on the bottom on your denominator. And then the math is the easy part, but the language is a little tricky. I wouldn't be really upset if I asked you a question about probability and you gave me a percentage. Like, I'm pretty sure I'll know that you did the math correctly. That's fine. But I might write a note like, hey, remember, probability is a decimal. Okay, there we go. And the second thing is that, okay, probabilities range from 0 to 1. So this is a little kind of an explanation about why probabilities are always expressed in decimal form. And think about, think about it this way. If we were to measure humans for something, just for anything, right? Measure humans on any level, for any on any variable, then if you get a one probability of something happening, that means that is the only outcome that happens. So like, here's how humans respond 100% of the time. That's the always on the spectrum. That would be a one. Can you think of anything that every single human would do as a response to some stimulus where we would get a one, which is an always for humans? I mean, you probably can't think of one because humans are so complex, and there's exceptions to any rule, even if they're tiny, even if they're a tiny amount of exceptions, they still exist, and that means that our probability isn't one always. Think about that. What a psychology class would look like if we, if we, if humans all responded the same way every time across situations to the same stimulus. It'd be like just presenting a classroom full of people things to look at and experience and go, see how you all reacted? Yeah, we all had the same exact reaction. I don't know. You can see how silly that would be, right? It doesn't make any sense to be like, hey, look, this is a whiteboard marker. And everybody goes, whoa. Be like, yep, that's how every single human responds to whiteboard markers. So always hard to imagine, right? Never, that's a little easier to imagine, that something might never happen. But that's where you go full stop on the other end, right? Because this thing's never going to happen. I always think about this in terms of like, say, like Halloween candy. If you're like me, I really love Halloween. I love it when kids come through the neighborhood all dressed up, they're looking cute. And then they knock on the door, they say trick or treat, to give them candy, right? So imagine like that scenario. You got your like big bucket of candy that you're giving out to these children as they knock on your door, right? Halloween. And let's say you got your two favorite types of candy. I'll just use mine. So mine are Reese's peanut butter cups and Kit Kats. So if I got those two, right? So I've got red candy. Let's say that's the Kit Kat. I got Reese's peanut butter cups. That's the, what was the packaging? Orange, right? So I got orange and red. So if I put like 10 Kit Kats in my little Halloween bucket for handing out candy, I got 10 Kit Kats, and then I got 10 Reese's peanut butter cups, right? 10 and 10. Then I would say, okay, if I close my eyes and I shake up the bucket and I reach in and I pull one out, right? What's the probability that I'm holding a Kit Kat? Well, there was a 50% chance that I would get a Kit Kat, just randomly, or there's a 50-50 if you use that type of language. Now you're talking odds, like 1 and 2, right? Chance that what I pulled out is a Kit Kat. And then probability would just be 0.5, right? Half. So there's half the probability, there's half the chance, there's half odds. So you're expressing the same thing just in different ways. And you can kind of understand the never and always in my little analogy too. Like if I only filled up my cauldron with Reese's peanut butter cups and I said, okay, I'm going to close my eyes and I'm going to stir up this pot of candy and I'm going to reach in and pick one at random, right? Not looking at all. Now, what's the probability that I actually pulled out Reese's peanut butter cups? It's the only option. So it's one always, right? It's always going to be one because that's the only, piece of candy that's in there. Now, the never would be saying, okay, I got like 20 Reese's in my cauldron and I shake it up. And I said, okay, now what's the probability that I'm holding a Kit Kat? You'd say zero because there wasn't an option, doesn't exist, in my population. That's a good way to think about, creating samples from populations, right? And how well does the piece of candy that you picked out represent all of the candy that's in that bowl? So that would be like sampling error, right? There's always potential there to get it wrong. Okay, let's move on. So, another thing about probability and proportions. This is something I just wish that I learned earlier on in kind of my career as a behavioral scientist. Is that really like probabilities and proportions are calculated the same way, and they express nearly the same thing. So you can use them, probability and proportions. You can rearrange your language to ask what sounds like an incredibly different or totally different type of question, but they're really not so different after all. Like if I ask the question, what is the probability of selecting a king from the deck of cards? Right? Well, you'd say, well, there's 4 kings and there are 52 cards, right? So it's easy to solve, but what I'm trying to focus on here is the language, not just how to solve the probability. So if you do the math, I just did it on my calculator. 4 divided by 52, it gives you a point zero 0.07. If we round it 7, so around that to point zero 0.08. So you got like a point zero 0.08 probability of selecting a king from the deck of cards. That's like an 8% chance, so it's not very good, right? Now, if you're asked the next question, what proportion of the deck of cards consists of kings, you'd figure it out the same exact way. You'd go, well, there's 4 kings, there's 52 different types of cards. So it's point zero 0.08. Again, the answer is the same, but I just wanted to point out the language that's used here because it sounds kind of tricky. It's like, it's asking you to do some totally different type of calculations to find the answer, but you don't. You use the same calculations for probability and for proportion. You just want to express um, them in the appropriate format. Is it decimal, is it percentage, or do you leave it as a fraction? And for our class, always go to the decimal. Okay, now let's look at some sampling techniques. So there's different ways to create a sample from the population, and you can imagine some are maybe more valid than others or higher in validity than others. And then really, the context that you're doing your research may dictate the type of access you have to people and how it is you actually draw a sample from those people, from that population, right? How do you actually create your sample from that population? So there's a couple different categories. There's the probability sampling category, and then there's the non-probability sampling category. So I'm going to look at these and kind of break down some different ways to collect data. All right. So remember, the goal for all of them is to minimize bias from sampling error and remove as much of that from your research as you possibly can. All right. So here's our big population, just a reminder, and we can't measure everybody. Say we're doing like survey research. We couldn't hit all these people with a survey. Instead, we pull our sample and hopefully it's a representative sample, but we need to pick some kind of technique. So in this black arrow here, right? What kind of technique should we use, which would be the best? So let's review. Okay, first, let's look at probability sampling. So there's some kind of thought and control here with probability sampling, but to different degrees. So the first is simple random sampling, where each member of the population has an equal probability of being selected for random sampling. So this might be like simple sampling. Usually, let's say we wanted to study all the students at BC, and we're going to do simple random sampling. What we want to do essentially is just make everybody know that our study is available. Our study is available, and we're going to send this out to like blanket all students, who are at Bakersfield College, and we'll just get the information back that we get from them. The advantages here is that it can reduce sampling error because it's voluntary, and the people who actually decide that they want to take your survey do a self selection. So the only thing you really have to worry about is two things really. um, did the people who volunteered, like self-selected to send their information back to you, do they all have something in common, like maybe about their personality or their demographics, so like their psychological or the sociological qualities about them that make them more likely to actually respond? And then you're only studying those types of people who respond to surveys, so that can be a problem. And the other thing, since it would be totally random, is like, what if people who don't, maybe there's a whole big demographic of people who like don't get back to you, so they're not represented in your sample. Like, would it be weird to you if we were looking at things that are going on right now with like the civil unrest and protesting going on in our country, and we did a survey about how is it that Bakersfield people feel about the Black Lives Matter movement, and we did simple random sampling, and we get information back. But if we did a deeper dive, could we find out that, you know, there's only one ethnicity that responded to us? Well, that might be a problem if we're talking about everybody, right? We need everybody's opinion in there, so we might lose out on some of that representation with just simple random sampling. And there's other ways to do this too, so we'll talk about those. So simple random sampling is relying on people to volunteer and self-select to do so. You might also do something like this, like systematic random sampling. So this would be, say I was reaching out to BC students to create a sample, and my population is all of BC students, but I'm going to base it on a sample, right? Instead of sending like everybody, every single student, one email with a link to my survey, maybe I pick like every fourth student. So everybody's in alphabetical order on some kind of, aggregated list. And then I just go, every fourth student gets the email. So not everybody does. And I don't look at who those, fourth students are as I go down my list. Don't care about the demographics. Like I want it to have, variation and randomness, but I want some kind of control just about how much data I have. So I'll send it to every fourth student, right? That's something else you can do, and researchers do that at times too. Okay, now let's look at something called stratified sampling. So in this case, members of a population are selected so they are equal to the proportion of that group in the population using random sampling. So let's say that, okay, I was going to look at BC students again, and there's three major classifications of ethnicity I'm going to look at, right? So maybe I'm looking at Black students, white students, and Hispanic students, right? So I've got my three different groups here. And then within each group, I would use a form of probability sampling. So let's say this first group here are my Black students in my drawing. So I go, okay, I need at random, like, 20 Black students. So I go, all right, so I'm just going to hit Black students and go like, all right, hopefully, 20 people self-select to get back to me and take my survey. And then you do the same thing for the next ethnicity, right? But what's important about this one is if you have more control. Probably if like for the probability sampling methods, this one gives you the most control because you can go, all right, I'm looking at like, quick facts, the demographics of the BC student population. And I know that I mean, I don't know if these numbers are accurate, so don't hold me to this one, but it's like something roughly like, 40% Hispanic, 40% white. And then we could say what's, 20% Black, something like that. That's not accurate, of course, but let's say that's what it is, right? Then in our sample, then we would want our sample to be 40% Hispanic, 40% white, and then where am I? 80, yeah, 20% Black, right? If that's what the population looks like, we don't want over representation of people here too, because you wouldn't like that very much, right? Like, what if, this is a topic that is you're very passionate about, and you look at who's in the study and you go, there's nobody like me in that sample, so I don't feel represented, right? And then also, it's good as a researcher to say, if someone, I had this happen to me once. I was at a different college, and this college only had like an entire makeup of the school. There was 2% Black students, right? Made up the population of the school. And so I did a stratified sampling method, and only 2% of my sample was Black. And then people were upset. They're like, you're excluding attitudes from our Black students. And I was like, no, 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 right? I collected a large amount of data so I could have, still a lot of input from the Black students, but I didn't want it to be representative in my sample. I want it to be reflective of the actual population. So that's good, right? So you have a reason saying like, hey, I'm not just like cherry picking data here. I did this on purpose, right? So you have a lot of control that way with stratified sampling. It's a good method. It's complicated. You need to know a lot of information about your participants, like from the get go, right from the jump. But if you do know that, then this is a really good sampling method to use. The disadvantages, it's kind of similar to just complete random sampling, only now you have these little groups of random samples. You know, you still have to worry about sampling error, especially if you're dealing with one of the groups that has fewer people in it. So in my example with ethnicity, we're going to have a lot more responses from generated from the white students and from the Hispanic students. And so there may be more variability within those two groups, and say it's their attitudes towards something, like more variability in their attitudes. And then maybe there's less variability from Black students who filled out the survey. Maybe there's less variability there. And that would mean that perhaps it means that we need more data from the group of Black students, but then we also then need to increase the amount of data from the second and third group, from the white students and the Hispanic students as well, so it's still an equal representation of the true population parameters. Okay, and the next one, whoops, and the last one for probability sampling that we're going to go over is called cluster sampling. And for cluster sampling, this is where you select individuals, um, into subsets, and then they are selected from. So it's like stratified sampling, but you're not controlling for like proportional representation. So it makes it really easy to choose people at random from your in this case like two groups. And looking at these orange dots in the slide, we've got these two groups here. It's really easy to choose from those two groups at random, but you would be missing out on some of that proportional control you get with stratified sampling. We might not know the information that's necessary to do a stratified sampling technique, like need a little like a lot of demographic info. If you don't know that, then cluster sampling might be the best you could do, right? Say in this case, then, since I was using ethnicity before, I'm just looking at two groups of students here. Maybe I'm looking at Hispanic students and Black students, right? And then so I go, okay, so I need to know if you're Hispanic or Black, and I can put you into two groups, but I'm not going to control for the size of the groups in the population. Right? I'm just going to use like equal number of, let's say I use like 100 Hispanic participants and 100 Black participants, and I don't control for population proportions and representation. Something to think about, right? Like when you see things on the news, but from polls and from surveys, you want to know like what was their sampling technique. Rarely is that spoken about, right, on the news. But it's a good question to ask, right? What's the representation like? That's a way of saying, what's the sampling error? How well does this sample represent the population? All right, let's move on to non-probability sampling. So with non-probability sampling, right now we're missing out on any kind of like randomness that might be necessary to avoid bias or sampling error. But in some cases, it's tough. It's really, really tough to do like legitimate random sampling, with proportional control or not. So sometimes you're going to rely on snowball sampling, for example. Now, in this case, you are cherry picking your data in a pretty big way, but it's usually when you have a very, very small population of people, and they're difficult to find for your sample, right? So you do have to do some kind of cherry picking just to find out where they are, right? Some of the arguments, like the sociological and social psych arguments about, maybe you heard this term like intersectionality. So that means like the different parts of your identity, they all meet at an intersection to make you who you are. Now imagine you have such a small niche group of people. That's not to devalue them as people, but there's not very many of them. That might be hard for you to find. Like if you're in Bakersfield and you're thinking, okay, I want to do a study about Black transsexual women who are between the ages of 20 and 25, right? Who, we could go on and on, who own dogs and live alone in an apartment. Like, how many people like that are there in our town, right? So once you find one person like that, you might go, hey, do you know anybody else who's kind of has the same demographics as you? Or that person goes like, oh yeah, my friend so and so, it's just like me on all these dimensions. And you go, oh, okay, can I have their contact info? Right. That might be a way you find your data. Oh, here's another example of that. So to get off the topic of like identity so much, what if you're doing a study about parents who have multiples, meaning like they have triplets or more, quadruplets, quintuplets, right? But anything more than twins. So those people might be hard to find too. I don't know if there's like a registry out there just to find people who have multiples of three or more. So what if you meet one person and that's true, and then they tell you, "Oh yeah, I go to this support group for parents of multiples." It's like, aha, right? Now that might be where I can find people I need for my study. So it wouldn't be random. You wouldn't just throw it out there and hope people sign up. You might be actually like going to where those people are, right? Okay. Now, then, and then sometimes that's okay. You just, of course, still run the risk of sampling error. All right, and the last one we'll talk about is convenience samples, and these are the most common for um, lots of the behavioral sciences, right? So a convenience sample, and just as it sounds, the members of the population are chosen, right, for your sample at convenience, and it's still on a voluntary basis, but you're just taking who you have access to. So honestly, the one I was talking about earlier with emailing all the students at BC, that's pretty similar to convenience samplings. It's who you have access to. But for most of, let's just take psychology for a second. Most psychology studies, I'm talking about published studies, right? Published research articles, most of them are done using convenience samples, and there are pros and cons there. The pro is that these students who make up most of the volunteers and participants in all psych studies, most of them are college students, right? They come from an introductory psychology course. You guys are going to school at BC, so you may have already taken intro psychology here. And we're not a research campus. So we don't have a lot of research going on. But if you took intro psych, even at the CSU level, CSU and beyond, you would have many opportunities to involve yourself in studies. It might even be part of the curriculum for an intro psych class. So when I taught intro psychology at CSUB, so I taught there for about 10 years, we would have a component of the class itself where either you volunteer for research or you have an alternate assignment that you do instead. And we did that because the psychology courses are usually really, really big. We're talking about like, well, for Bakersfield standards, 100 plus, students in nearly every intro psych class. So you can get a lot of data really quickly. That's a pro. That's an advantage. The other advantage is that in an intro psych class, it's gen ed. So there's all different types of people in there with different interests and different backgrounds, different ages, ethnicities, socioeconomic status, and so on, right? All within that one class. So it's a good mixed bag, of people. And that's another advantage, right? So you have some variability in there among your participants. The disadvantage, of course, is that they may all have something in common. What if it's a class at night? Is there something particular about students that only take classes at night? Maybe there is, right? But that'd be one kind of bias you'd want to try to control for. Or maybe the big bias is just that all of these participants are college students, and maybe all college students have something in common that would skew the results of your study and create misleading outcomes, right? So that's something to think about too. And that's an argument from people often about psychological research done on college campuses. They would say, yeah, but does this pertain to people who are not college students, right? Does it pertain to them as well? Does it represent them? Valid question, right? And that's kind of the problem with convenience samples. They're convenient, right? That's why they're called that. Those people are right there. You can survey them. But the disadvantage is, of course, that the sample may not represent the population due to this selection bias because there's nothing random about it. Okay. So sampling error is another way of saying there's something biased within the sample. It was done during a selection, technique. Um, that was cherry picking the data, and the researcher either did it on purpose or just, overlooked it. Um, and the second way is just kind of sheer bad luck. You can always control who signs up for your study. The example I used earlier about intelligence. What if only doing the study in college and only the students that had like a 4.0 signed up to take your study? It's like, well, are we talking about every student or just the 4.0 students? I wonder about that one with I teach a human sexuality class, and the papers I get in that class, for whatever reason, are all typically all really, really thoughtful and well written, and well researched, and the citations are correct. And I think, okay, compare that to when I teach intro psych, and there's just like a huge amount of variability about how well people write. I think, why is that? Why is it in this human sexuality class it's just a breeze and a joy to read these papers, and if I write anything on them, it's like, oh, good point. I never thought about that. It's more about the content. It's like, would there be something about taking students only from my human sexuality class that are different from the college at large? Would it no longer be random? They have something in common. So random sampling is a technique to help you get around all those types of sampling errors, but it's still never a given. And ultimately, if you're really afraid that your results from your study are due to sampling error, you could replicate the study and run it again with a whole new, batch of participants and see if you get the same or different results. Right? The other thing to think about are events are independent. So that means, in this case, let's say an event would be collecting data from one person or from one group of people if you're collecting it from them all at the same time. You don't want like their data to be skewed by anything, right? And then you don't like, here's a simple example of that. You say you're doing research the survey research the old fashioned way, and you have participants come into a room and they fill out a questionnaire, a survey, and then they leave the room, and maybe as they're leaving, like, the next group of people is waiting for their chance to come in the room to fill out the survey. And that first group walks out and they go, oh man, you're going to love this study, it was so much fun. Here's the hypothesis, here's what the study is all about, right? And then maybe you don't want those new participants are coming in to know any of that. It might skew their answers somehow, right? So I mean, that's like a kind of seems like a silly example, but it could happen easily, right? Then your events would not be independent from each other. This is why too you might do a blind study or a double blind study. Have you heard those terms before? But like, a double blind study means that the participants don't know what condition of an experiment that they're in, so they don't know if they're in the control group or some experimental group. And then also the researcher doesn't know if those participants are in the control group or the research group. And that can be a good thing because the researcher themselves, they can create bias within the study and how they interact with participants. Got like two stories I'll tell you about that. So I was a McNair scholar, is what it's called, and when I was a CSU student. And that basically meant that I produced some kind of research that this foundation considered scholarly and publishable, that kind of thing. And so I won this award, and created opportunities for me, which were amazing. So I got to tour around to university campuses on like every break from school, so like the winter break, spring break, summer break, and kind of go into a research lab and basically learn how they do research, to go observe or sometimes even be hands-on. Really cool. So I went to one at the University of Texas El Paso at UTEP, and what they did there is they were testing a new antidepressant drug. So they developed this new antidepressant and they were testing it on humans, and they just had me and another volunteers or interns, essentially is what we were, had us, they trained us how to, and then we collected the data from the participants and entered it into analytic software. That was about it. But we found out, oh, here's the setup. So they had people who were getting a placebo of the drug, right? And then they had, no, that's a different study. They had people without depression at all. They had people with moderate levels of depression. They had people with severe depression. Okay, now they came in to the lab just to fill out surveys about how they're feeling. So it was like a, self-selection, self-report style survey of, their own emotional state. So they would come fill those out. And at the very last day, where like the department and the lab we're working in, they kind of threw all of us a lunch. There was like 12 of us interns, threw us a lunch to say thank you for helping us with the study. And it was really fun. We really liked each other and we got to say goodbye that way. And then they did this presentation where they showed the rooms where people were coming in to fill out the surveys. And they showed me on the camera. And I thought, wait a minute, I didn't know they were filming us. Nobody ever mentioned that. And they didn't tell us because they didn't actually create a new antidepressant at all. Um, Instead, what they were observing was how the experimenter interacted with the participants. So they were looking for experimenter bias, right? They fooled us. And they wanted to see if we treated people differently, with the knowledge that they either didn't have depression, had like a low level of depression or a high level of depression. And to be completely honest, I was the worst. So I treated people very differently, based on their level of depression. It was like comical. You could see it on the video. By the people with no depression came in. It's like, thank you for your time and filled the survey. Here's information about debriefing. Here's who you contact and so on. And then like the time I got to like the severely depressed group, I was like smiling more. I was like really engaged with people, like trying to make a connection. But I wasn't trying is the point, right? I was acting that way. And if you asked me, I would have said, I think I treated them all the same. I think I treated all three groups the same. But it was pretty clear that there would be some experimenter bias. And it may impact, the results from those self-reports. And the second thing about events being independent too, this comes down to methodology again. You have to watch if you're going to use, even through like electronic surveys, you got to be careful in the language that you use when you ask questions. Um, so, for example, I helped evaluate some implicit bias training at the state level some years ago. And the way that they presented this, which essentially was like mandatory, mandatory training everybody had to go through. But, like you might have to go through like sexual harassment training at work. It's the same kind of thing, where they're watching videos and then they're answering questions. But the way it was worded when it was sent out to everybody made it seem like by, receiving that email, because it was like automated, they just like plugged everybody's name in who received the email. It made it seem like all those people had done something, to get the attention of like human resources, and they were being sent this training as like, some form of rehabilitation, or they're being reprimanded for something. And so people came in pretty defensive, thinking like, why do I have to do this? Why do you think I have this bias? Why are you calling me out? And that affected how they responded to the training. So in that case, then the IV and the DV, you know, are muddied. They're lacking in some validity for sure, right? All right. So in that case, events would not be independent. Okay. So the last couple things for this chapter, this is where kind of we're not going to do a whole lot with this in this chapter, but we will later on for sure. We'll do a lot more. So when it comes down to getting into hypothesis testing, which we're going to get to next in a couple weeks, here's a graphic that you don't have to memorize these numbers. Don't worry about that. These numbers on the x-axis, but this will show you the proportion of scores, under the curve. So under the blue line, under this blue line here. So proportion under the curve. And you can see, okay, the probability of randomly getting a number is in the segments here. So if we look just from 0 to +1, it looks like 0.3413. That means there's a 34% chance, or 0.34 probability of getting a number that falls within this range if you're just to pull a number out at random, right? Remember my example about candy, you know, in the Halloween bucket? right? You would say like, okay, well, each one of these segments is a different type of candy, right? And these candies are in there the most, right? Between 0 + 1 and 0 - 1. There are more of these candies than any others. So, of course, you're going to get more of those. And as you move away from the center to the left or to the right, then you see there are fewer and fewer of those types of candies as the frequency goes down on this graph. And so the probability is going to go down too, right? You're less likely to pull out, let's say it's a Snickers, uh, 0.1359 probability or like a 14% chance. If there's only 14 out of 100 of those candies are Snickers, right? That's what this is telling you. So this graph later on will be this distribution later on will be really handy for us in understanding the amount of probability if a score lands into this area, right? If a score lands into this segment, for example, if we go as far as we can, +3 and beyond, we're looking at 0.0013. Like these scores barely even exist in the population, right? They're barely there. We want them there in our sample. But we don't want very many of them if we're trying to be proportionally accurate, right? Okay, so the good news about this, like I said, you don't have to look this up. There's a table in the back of your book. And I think what I'm going to do is I'm going to scan the table and just put it up as like a PDF on our page so you have easy access to it. So you might end up doing like a mathematical formula because I want to know what's the probability that a score falls within this range. Then you can just look it up in that table in the back of your book. But we'll get to that. We'll get to that probably the week after next. Oh, and by the way, I forgot to say this. This is called the distribution of sample means. And the idea here is that instead of, this distribution being made up of just individuals' scores, it's made up of averages, right? Um, so actually, let me illustrate that for you. All right. So here's the basic idea. You have, let's say we have a distribution. Oh, let's take, we have a lot of high schools here in the Kern High School District. Let's do that. So let's say we're going to look at one high school. I went to school here and I went to East Bakersfield High School. So let's say here is the bell curve for like some standardized test score at East. Let's say it's like, I don't know, verbal communication or something like that. So we can get, all these individual scores will be all X's, right, along this X axis. And then right in the middle, we have the average score for the students at East, right? The X with the bar over it. So let's say here, this is EBHS, right? Here's the frequency, and here are our test scores. That makes sense, right? You have all these individuals. Some individuals are going to perform better than others. Some individuals are going to perform worse, right? And then we can find an average right in the middle. And we can say, oh, half of you are above this average, half of you are below, right? And that's what East looks like. And then maybe for the entire high school district, we have, instead of a bell curve made up of individual scores, we have a bell curve made up of averages, right? So we're just going to take multiple averages and plot them into a distribution, and we'll get another curve because some schools as a whole will do better than others. Some schools as a whole will do worse than others. And then some schools, many of them will be kind of like right within this kind of average range, right? We're going to find the most schools fall within this range. Some are going to outperform other schools, some are going to underperform. And we might want to find out why, right? Why is it that these schools are, performing better, and why are these schools not performing so well? So this would be like the entire Kern High School district. And then each one of these X values, now I'm not showing any favoritisms. I don't actually know the answers to these scores, right? Let's say here's EBHS, and then let's just do all of the directions, right? Here's west. So we got east, west, we got south, and we got north. And then we'll throw in some others too there. Here we got like Centennial. And maybe over here we have like Foothill, right? So from each of these schools, we can get an average made up of individual scores. And then we can take all of the schools' averages, this number right here, and we can make another distribution full of averages instead. And what we'll find is that within this range, most of the schools will fall within this range. But some schools will outperform, some schools will underperform, and we should get a bell curve for that too. So if all of the schools at one school side at a time are giving us these nice normal curves, we put them all together, guess what? We're probably going to end up with a nice normal curve at the end. Okay, now the last thing for this chapter is, after talk about the distribution of sample means, which we'll come back to again, we'll revisit that again, is something called a confidence interval. And this gives you a range of values, like it says here, that the population mean is likely to fall into with a specific level of certainty. So it's like saying, okay, my sample average from this pop distribution of sample means represents all schools within this range, or all population scores within this range. So let's say it's South, that's like right in the middle here in my distribution that I drew before, right at that 0 mark here on this graph. So there's one high school right there, South. And you could say, okay, the average score from South represents like any high school that falls within this range, plus or minus 1 above that mean. That's kind of what we could figure out with a confidence interval. And we will come back to that idea. We're not even going to calculate one today. I just want to kind of plug that seed, plug that language into your ears, into your brains right now, so that when we do talk about it later, it won't feel like we're just coming out of left field. You can go like, oh, I've heard that term before, right? Okay, guys, so I'm going to post this lecture to Canvas now. Do watch the other videos that are up there, because they're also very good. I've watched them all, hand selected them for you, because I thought there was something useful in them. And don't forget to take all the quizzes and all the associated assignments with the chapters we've covered so far. All right, I will see you all later, right? Maybe you'll come to my office hours. Yay. Bye.